In the previous unit, we discussed the handling of variables. Now, these variables appeared in the context of expressions, and I kind of waved my hands around the translation of these expressions into VM code. Well, in this unit, I'm going to discuss this translation in detail. So we're going to talk about how the compiler handles expressions. Now, to get started, I'd like to go back to basics and present to you a subset of the Jack grammar that describes or defines expressions. And here I simply lifted a snapshot from the book that accompanies this course and simply put it on the slide. And what we see here, once again, is the grammatical definition of what it takes to be an expression. Now, we discussed this in the previous module. I'm not going to repeat it, but I just want you to observe that every one of the expressions that we see here will qualify as a legitimate expression according to this grammar. For example, take the number 5. Well, I look at the grammar, and first of all, I observe that 5 is an integer constant. Now, if you look at the second rule, you will see that an integer constant is a term. And according to the first rule, a term is an expression, and therefore 5 is an expression. What about x? Well, x is a variable name. And according to the same second rule, a variable name is a term, and term, once again, is an expression. What about x plus 5? Well, x is an expression, or x is a term, and plus is an op, and 5 is yet another term. So once again, it matches the pattern of term followed by an optional op and yet another term. So using the same rationale, every one of the expressions that you see here will qualify or will be accepted by the Jack grammar. Now, as you can imagine, I can invent an unlimited number or an infinite number of such expressions, and some of them will be highly complex. And the question that we face as compiler writers is how can we systematically translate any one of these versatile expressions into VM code. You know, beginning with a trivial 5 or x and ending with a very elaborate expression. How do we do it? How do we map it on VM commands? Well, the first thing that we have to bring into the picture is the parse trees that we mentioned and used in the previous module. And what we see here is an example of a simple expression, a times b plus c, and the parse tree which can be derived from this expression, or the parse tree that describes the same semantics that the expression describes. Now, this thing is called infix. This notation is called infix. And as I pointed out here, it is human-oriented. What do I mean by this? Well, look at b plus c. We want to add up two quantities, b and c. Why do we say b plus c? Why don't we say something like add up b, comma, c? Or why don't we say something like here are two quantities, b and c, add them up? Okay? Instead, we say b plus c. Why do we use this language? Well, we use this language because that's what was sort of ingrained into our brains in elementary school. We were taught that whenever we have to add up two numbers, we say the magic words b plus c. And because the operator is located in the middle of this expression between the two operands, because of that, this notation is called infix. But you have to realize that there's nothing special or sacred about this notation. And this notation will be just as good. In prefix notation, we put the operators before the operands. And that's why it's also sometimes called functional notation, because that's what we do when we define functions, right? We put the function name, and then we give a list of operands or parameters or arguments for this function. So here, for example, we start from the left if we evaluate this prefix expression, and we realize that we have a multiply operator. Well, we know that multiplication is a binary operator. It expects to see two operands. So we keep on reading, and we're looking for the first operand, and we find it. It's called A. And now we look for the second operand. Well, we hit this plus. So we know that the second operand is the result of applying plus to two more arguments. And so we go on to evaluate the plus and so on and so forth. So you see that the prefix notation is just as natural and ubiquitous as the infix notation. And if you don't completely see it, you can add some parentheses and then things will become clearer. Finally, we also have something called postfix notation. In the postfix notation, we first list the arguments on which we want to operate, and then we call up the operator that has to be applied to the previously stated operand values. Now, for obvious reasons, this is called postfix, and I would like to point out, very importantly, that this postfix notation is intimately related to our stack machine, because our stack language is also postfix, right? If we want to add up two numbers, what do? We push A, we push B, and we say add. Classical postfix. So if you take everything that you saw in this slide into consideration, except for the prefix, which is irrelevant for our discussion. So if you think about the infix, the postfix, and the pass tree, this gives you a very strong clue on how you can translate from infix to postfix. Now, why is this important? It's important because our source language is infix. Java, C#, C, Pascal, Python, all these languages are infix. You describe expressions using infix notation. And yet, at the same time, our target language, the VM language, is postfix. So the compiler has to translate from infix to postfix. How should we do it? Well, I guess that you are beginning to guess the answer. And here is one way of doing it. We start with some infix, we start with some expression written as usual in infix notation, and then from it we generate a pass tree, okay? And by the way, how to do it is something that we've already done. That's what the parser is all about. That's what we did in the previous module. We wrote a parser that takes source code like this and produces XML code from it. And XML is just yet another way to describe a pass tree. So you put together this pass tree, and then you go through every node in this pass tree in a certain order, and you generate from it what you see here on the right-hand side, which is stack machine code that can be executed, and this execution will result in evaluating the value of the source expression, which is exactly what we want, right? Now, if you're not convinced, I suggest that you stop the tape right here and go through the stack machine code and convince yourself that this code will end up computing the code that we started with, the source code on the left. Now, the question, of course, is how do you move from the pass tree to the VM code? Well, there's an algorithm that does it, and this algorithm is called depth-first tree traversal. And so you begin from the root of the tree, which happens here to be the symbol plus, and you go all the way down, and when you hit a terminal leaf, you process it. So you go all the way down and you found X, well, you output push X. Then you backtrack to the root, and you once again go all the way down, and you'll get to the 2. You push 2. You backtrack to the closest node, which is G. You go all the way down, and you push Y, and so on and so forth. Now, I don't want to spend too much time about this algorithm for 2 reasons. First of all, we're not going to use it. We'll use something different. And second of all, notice that the parse tree of a real program can be gigantic, right? All we have here is a very simple example. And therefore, it will be nice if there were an alternative way to process this parse tree or to process the source code without creating the entire parse tree as a side effect of this code generation operation. Indeed, there is such an alternative, and that's what I want to discuss next. In the algorithm that you will see here, we're going to generate the VM code on the fly without having to create the whole parse tree in the process. In particular, we will use the following code generation algorithm that we called code-write. So code-write receives an expression and goes on to generate code from it. Now, if the expression is a number like 5, the last token in this input example, then all we do is output the VM statement push 5, or if you want to be accurate, push constant 5. If x happens to be a variable, like x, the first token in this input, then we output the VM command push x. And of course, we don't push x, we push something like local 0 or static 2, whatever is the mapping of x on the virtual segments as dictated by the symbol table, which is always in the background of these code generation algorithms. If x happens to be the expression exp1 op exp2, for example, a plus b, or in this example, x plus g something, then first we generate code for x, then we generate code for g in this particular example, and then we output op, okay? And we do it because that's the way that the VM code works, right? We want to transform the infix operation into postfix, and that's exactly what we have just done. Now, if x happens to be a unary operator, an op followed by some expression, for example, minus x in this, it's minus z in this input sample here, then first we generate code to evaluate z, and then we output, in this particular example, neg, which is the VM way to describe minus, when minus happens to be a unary operator. And finally, if exp is an invocation of some function, for example, g applied to 2, y, and minus z, then first we generate code to evaluate 2, then we generate code to evaluate y, then we generate code to evaluate minus z, and only then we output call f. And this will apply the f function on all the values that were previously evaluated and placed on the stack. So as you see, this very elegant and highly recursive algorithm is well equipped to take any infix expression and convert it into VM code. The result, in this particular case, will be the stream of VM commands that you see here. And if you are not sure that this is the case, you can play with the algorithm, stop the tape, and convince yourself that indeed this will be the output that this code generation algorithm will generate in this particular case, in this particular example. Now, the nice thing about this algorithm is that not only does it capture the semantics of the input expression, it also computes the value of this expression So in runtime, the value of this expression is going to be placed on the stack, and that's exactly what we want to achieve. So things look fine. And with that, I'd like to turn to make some very important points about the switch from parsing, something that we did in the previous module, to code generation, something that we do now. So here's another example of some input source code or some input expression in the context of a let statement. And if we would apply the compiler that we wrote in the previous project to this expression, then we will get the XML code that we see here. And what we see here is a rather sort of flat expression of the input. We say that we have the identifier A, followed by plus, followed by the identifier B, followed by minus, followed by the identifier C, and so on and so forth. We go from left to right, and then, after we compute the value of the expression, we add some XML tags, and that's it. So we generate static XML code. That's what we did in the previous project. But in the current project, we do something quite different. We generate none of the XML that you see here. This XML is completely irrelevant now. And instead of generating it, we generate actual executable VM code. Now, a great deal of the program that you wrote before is applicable. I mean, the overall API and the overall structure of the compiler or the compilation engine is applicable also to this project, but the part that generates the XML code has to be replaced with code that generates this particular example here, the VM code that you see at the bottom, or something similar to this VM code, because different compilers generate different target codes. Some compilers are more efficient than others, so I cannot tell exactly what your compiler will produce. I can just give you some, general guidelines on what has to be done. So these are that's the first observation about the difference between what we did in the last project and what we do now. I'd like to turn your attention to yet another example. Instead of A plus B minus C, we now look at A plus B times C. What will the code generator or the previous algorithm do with this expression? Well, it will happily produce the VM code that we see here. It will push A, it will push B, it will add them up, then it will push C and multiply the result C by A plus B. And then, obviously, it will pop the result into X. So that's very nice indeed. However, as you hopefully saw, this VM code will not generate the correct algebraic result of A plus B times C. Why? Because we have what is known as operator priority in mathematics. So first we have to compute B times C, and then we have to add A to the result, given the operator priority of mathematics. The compiler is going to ignore operator priority and produce this code instead. That's one possibility. I called it version 1. Another compiler, written by perhaps a different student or a different developer, may well produce this version, which happens to be, in this example, algebraically correct. Okay? So what's the difference between version 1 and version 2? In version 1, we go from left to right, and we look at this expression as A plus B times C. So we associate operators to the left, so to speak. In the second version, we view the input as A plus B times C. Okay, so we evaluate A, then we evaluate B plus C, and then then we evaluate B times C, and then we apply the addition operator. So the question is, which version is correct? And the answer, surprisingly enough, is that both versions are perfectly okay compilation-wise. Why is that? Well, this peculiar observation is due to the fact that the Jack language does not have operator priority. There's nowhere in the Jack language specification will you find a rule that says that multiplication comes before addition. It's not there. And it's not there because we decided, Noam and I, when we designed the language, we decided to design a language that has no operator priority, because a language like this lends itself more easily to writing a compiler. So it's the job of the compiler writer to decide how he or she wants to pursue this expression. From left to right, from right to left, we don't care. Okay? So operator priority is not part of the language specification. It's part of the implementation. It's up to you to decide how to carry out this expression evaluation. That said, obviously, we have to allow Jack programmers to give them the ability to write programs that are algebraically correct. And therefore, we allow or we feature in the language parentheses. And the Jack programmer can use parentheses to signify or to inform the compiler that he or she wants to evaluate b times c before evaluating the plus. So it's the job of the compiler in this case to generate only this particular version. If there are parentheses, they have to be respected, and so we have to view this expression as a, that's exp1, plus b times c, this is exp2. So we evaluate a, or we generate code that evaluates a, then we generate code that evaluates b times c, and then we emit the add operation. Okay? So once again, in the first example that you see at the top, the compiler can generate one of these two versions, and it's kind of indeterminate. But once we have parentheses, we must, the compiler writer must take notice of the parentheses and cause the code-write algorithm to work in the proper order, as dictated by the parentheses. All right, so this is everything I wanted to say about compiling expressions, and we are now in a position to move on and talk about flow of control.